Hey, welcome back. In this video, we're going to talk about a very specific exponential application called half-life. So I'll read this context right here. We'll back up, talk a bit about exponentials, and then we'll attack this question with our knowledge of exponential functions. In this example, we're being told that cobalt-60 has a half-life of 5.3 years. Then we're being asked, hey, then if we had 60 milligrams of a sample, how much of that would be left in 12 years? First and foremost, or importantly, is this statement right here, the idea of half-life of 5.3 years. Now, I'm not going to sit here and act like I know the deep intricacies of the idea of half-life, but what this means simply is that if you have a certain amount of this cobalt-60, the radioactive decay of that isotope that you have, you'll have half of it left after 5.5 years. So if we had 100 milligrams, we start with 100 milligrams, 5.3 years later, you look at it like, what happened? We only have 50 milligrams. And importantly, this idea of a factor, this factor of a half, invokes the idea of exponentials. So just to remind us real fast, we have these general exponential setup where it's a times b to the x. The a right here is always this initial amount, and the b is this exponential factor. Beautifully, in this case, we actually can use this exact same setup and just modify it a little bit, and you'll see this. But it's this initial amount. We still can start with our initial amount we have. That'd be like the 60 here. And this factor is actually told to us also. In this case, the factor would be 1/2. So I'm going to set this up real fast, and we'll set up a model for this cobalt. So the amount of cobalt over time, and t in this case, time will be in years. And we can change this based on the information, but since they said the half-life is in years, I'm deciding that everything from now on, this function I'll be using is in terms of years. But we have this initial amount, so we have the 60 in this case, and again, this will always be that initial, that a value in our general exponential function. And now we know our factor is 1/2. The thing here, and this is a really important trick when you're setting these functions up, is that if I put 1/2 to the t right here, what that will do then is apply 1/2 or take 1/2 of my amount every year, whatever I have t set to. But what I'm going to do in this case is write it as t divided by 5.3. And the important reasoning of this is then what this will do is only apply a factor of 1/2 once the t value reaches 5.3. And so this little trick right here will make sure that the factor of 1/2 is only applied every 5.3 years. Now, obviously, if we see this as a continuous function where t can be any value of years from a fractional amount to a whole number amount, this will take care of that also. But again, if you think about this, if we inputted t equals 5.3, we would get 5.3 divided by 5.3, which would be 1. And that would multiply then, we'd get one factor of the 1/2 and multiply the 1/2 by the 60 as we expected. There are a couple different ways to actually set up this exponential function. You might see in your textbook or in other resources different ways of doing this. For me, this makes the most sense in the way that I always describe this. Because again, it's exactly the same as this general form of an exponential where I have an initial amount and a factor. The important thing again is this adjustment to the variable up here in the exponent. In other examples, you'll see ways that we'll do that. But in this case, if I don't want this to double every year, but every 5 years or 6 years, whatever that number of years is, I divide by that number to make sure that this 1/2 is only applied once this reaches 5.3. And again, that's just thinking of it in a discrete way. I could put half a year here, and this will take care of all of that for me. One thing I also want to talk about is if I wanted to write this in a way where I didn't have this fractional expression here, I could rewrite this. So I could write this as c of t equals 60. Now what I'm going to do is rewrite this. I'll do this in 2 steps. So we'll have 1/2, and I'll write this as 1 over 5.3 times t. So all I'm doing is splitting apart these factors. Here's t times 1 over 5.3 this equals that. And then if we just apply our properties of exponents, this right here, the multiplication of these exponents, I could rewrite this as 1/2 raised to this power raised to the t. And you'll see the reason I'm doing this in 1 second, but this could be written as 1/2 raised to the 1 over 5.3 raised to the t power. And these expressions are equal because when I have this, I raise an exponential to an exponent, I multiply those exponents, and I'm just going backwards with that process. And then if I calculate this, 1/2 to the 1 over 5.3, I get that this becomes 0.87741 to the t. And while that might just seem like a fun mathematical exercise, that's actually really important. What I've done, given this information and this setup, have this factor of 1/2 every 5.3 years. In doing this work right here, I've actually written this in terms of per year. And importantly, if I read this, what this says is now every year we're going to apply a factor of 0.87741. And always I use a lot of decimals when working with exponentials, just so I get a fairly accurate final answer. But importantly right here, this means we have 87.74% of the original per year. Or in other words, that means that we lose, or it decays, I guess would probably be a better way of saying that, of 12.26% per year. All right, so we've done the work of creating the model which represents the amount of this cobalt-60 left after t years. And importantly, and you'll see in the examples, you always need to be aware of what your t value represents. In your information, you can be given years, days, minutes, hours, then ask questions with different units. You need to make sure you make the substitutions necessary to work with your function in the way that you need to. But importantly here, we were told about years and we're given a question about number of years. Everything is good. Now I can use either one of these models. Generally speaking, I will always create this version of the model. It's a little bit easier to work with. Not a ton, but especially when I need to solve for like t, I find this to be a bit easier. But either way, we move forward. We're being asked about the amount of this after 12 years. And so now that we have our model, all we need to do is find C of 12. This will find us the amount of cobalt after 12 years, given an initial amount of 60. 0.87741 is the yearly factor, and we're looking for 12 years. And then in computing this, I just need to evaluate this first, raising this exponential factor to 12, and I got 0.28 or 20817 thereabouts. And then when I multiply these together, I get 12.49, and this is calculating in terms of milligrams of this cobalt-60 that we have left after 12 years. Again, just a quick review of what we did there. We created this model. This is the initial amount of 60 right here, whatever the initial amount that we have. We decided that T was in years because the information we were given about the half-life is in terms of years. The 1/2 right here is because we're talking about half-life. This division of 5.3 because every 5.3 years. And finally, we can do the work to find the yearly rate if we apply that division of 5.3 as an exponent to that 1/2 to get this yearly rate form of the half-life equation.